Maybe with that hindsight, you could say, I didn't need to look ahead. But I needed to make sure that that would be the outcome. So that's my admission saying that I have looked ahead. I know when I start, I know what questions I'm going to get because I have to look ahead to make sure that it's not one of the two questions that I've already done. But with that confession, what I will still claim, assert, is that I haven't had a lot of time to think about it. I do know it's some sort of a square wall question. Again, I've seen it, but I didn't read it carefully, other than making sure it's not one of the questions I've done. And didn't really have time to think about it. I was busy editing the video and doing the other stuff. So as I start this freeform timed assessment demo, it'll be a fairly genuine attempt at trying to do this question in within the 20-minute time limit. And again, no outside help, no ChatGPT. I'm not using it right now. You should not be using it. And you know, it's all practice anyway. So why would anyone cheat at practice? So let me start, and I'll make sure I don't go over the 20-minute time limit, assuming it's not overly difficult of a question. So start. I have a clock here to help me keep track of time. Start. All right. So as I was saying, you know, it's a square wall question. Consider a particle of mass, a square, infinite square wall. Again, as I was saying earlier, finite square walls, we can only do it at a conceptual level. It'll be so time consuming at any quantitative level. Step potentials different. Finite square wall, too hard, too much. Okay, potential goes to infinity. Enter text sensors. Yeah, okay. Figures. Yeah, pretty to describe it. I'll write anything down here. So write down the time-independent Schrodinger equation for the energy eigenstate wave function with this region. Write down the boundary conditions. Okay. So I can, let me just write it down. I actually have a Schrodinger equation memorized. And the way I have, so let me write down the memorized version. The time-independent Schrodinger equation says minus h bar squared over 2m, the ordinary derivative, second order, with respect to position, plus the potential. I guess I can write it and then cross it out later, is equal to energy of the state. And the way I have this memorized is by remembering this operator form, that momentum squared over 2m plus the potential energy is equal to the total energy. Kinetic plus potential is equal to total. And this is really supposed to be an operator. For the time independent, energy is just a number. And the way you make sense of the operator is by acting on the state. So this is what I have remembered, and I also remember momentum is h bar over I, partial derivative with respect to x. So that's the equation I have remembered. Now, here the potential will be 0. So this whole term is 0 in the range from 0 to L. So Schrodinger equation is minus h bar squared over 2m times times the second order derivative. So I guess I could write this d that psi over dx squared. Yeah, it's fine. It's equal to e times psi. The boundary conditions. The boundary conditions at x equals 0 and x equals L are the continuity of psi x. So psi x equals 0 or L is equal to 0 from inside the square well, because immediately outside psi x goes to 0. Let's see, did that answer everything? Okay, find the wave function solutions to the Schrodinger equation above for the three lowest energy states. Find. Yes, if you know them from memory, that's fine. So let me write them down from memory. So they are all gonna be in the form of, let me use real functions because they are bounded states. You have real solutions. So So let me sketch out what the solutions look like visibly. So visually, if these are the first three energy levels, not drawn to scale, then the wave function solutions kind of look like this. This is the lowest energy. This is the next lowest energy. This is the next lowest energy. Each time you add a node as you go to the excited state. And all these forms of solutions, they can be expressed as psi of x is equal to, I guess if x is equal to 0, then I can describe all of them with a sign. So it'll be a of sine of something x. For the time independent solution, for the time dependent solution, you tack on the predictable time evolution factor. So it's really what comes here. And what comes here, I could say that's kx and then describe the k. Or I could kind of figure it out. For the longest wavelength, it has to be, let's see, I think pi over L. So that when x is equal to L, it's a sine of pi, which is 0. And that's the first time x became 0 since 0. To get the next one, here it should be 2 pi. So as you look at it, you then figure, oh, I can have n here, where n goes from 1, 2, and so on. So that's my basically remember the solution. And I could say I derived it, and the way I derived it is by guessing it. And then I think I'm going to be checking it by plugging into the Schrodinger equation maybe. So psi of 1 x is equal to a times sine of... Did they tell me to normalize it? Not yet, so I won't normalize it yet. If it later tells me to normalize, then I will. Times x. Oh, wait, here n is equal to 1. That's psi of 1, or the first solution, and the next one you just swap the quantum number. The energy levels. So you couple different ways you can do it. You can do it by plugging this solution into the Schrodinger equation that will give you the energy levels. Or you can kind of, this is the approach I used in the lecture, and nothing stops you from doing it. You can figure out, well, energy is basically going to be kinetic energy, which is p squared over 2m. So you just work with the allowed momentum values. For that, you could actually say p is equal to h over lambda, and here lambda is equal to 2l, lambda is equal to l, lambda is equal to, I guess that's a 3l over 2, I think. No, the other way. Lambda is equal to, it's shorter than l, so it's a 2l over 3. So it's there's a pattern to lambda actually, so lambda n, just looking at those three, it should be like 2l over n. So putting all of this together, you would say energy with the quantum number n is equal to p squared. So h squared over lambda squared, which is n squared h squared over, I have rest of this, so 4l squared times 2m, so 8ml squared. And that matches the energy levels that I do have memorized. I remember that factor of 8. That's the main thing I remember. E1 is equal to, so plugging in 1, it's h squared over 8 times m times l squared. And then I have E2 and E3. So for 2, it's going to be 2 squared, so 4. And I'll just leave it unsimplified. I think it's fine. Let's see. Sketch of the solution in attached work. I would have plugged it into Schrodinger equation if asked to show these guesses to be the solutions. All right. Part C. Sketch the probability density. For the 3 states you found, put the answer below, give the... Right, so let me sketch them first. So I can kind of refer to that picture of these are the wave function. And what I now need to sketch is the wave function squared. So let me do that. So this is the potential well. And what I'll be plotting is the wave function squared. And you can kind of see with all these how it should work out to be. Let me just draw the zero line for each one of those states. The ground state should be the easiest one because it's the simplest. The one in the middle, it just becomes some value. Really, the feature that I see a lot of people miss is what happens at the end. Because here, the end has a slope that's non-zero. And that's allowed because your potential suddenly goes to infinity. Now, that approximates to a line. When you square it, that approximates to something that's a parabolic, which means for the absolute, for the psi absolute squared, really near the boundary, the slope does go to zero because it's going to be like, so it'll look something like this. And the reason for that the reason for the zero slope at the end will be that it's a squared thing. So the it's parabolic. The slope at that point is zero. You have to make sure you have that. And then after that, so I just need to have the node and just to make sure it looks like the sinusoidal thing shifted up. So this is the n equals 1, n equals 2, and for n equals 3 nodes. It's not kind of normalized or anything, so just make sure it's a sinusoidal thing with enough of an offset so that it never goes into negative but does touch the zeros at where the nodes were. So that's my sketch. I might have to move it down a little. Okay. Sketch the probability, give succinct the psi x absolute value squared still looks like a sine wave, but with an offset, so it never goes to zero. At the nodes of psi x squared does come to zero, but with a zero slope, like the bottom of a parabola. Sine wave, but with an offset, so it goes to zero, and also double the frequency. Like here, n equals 1, before it was half of a wavelength. This is one full cycle in psi squared. So I think sketch itself is attached. All right, part D. Three-motor square well at an infinite square plane approximation. Finite square. Oh, all right. What am I asking? I hope it's only conceptual questions. List. Okay, it's conceptual. I'm not gonna be able to solve it. 3 significant changes to the solutions as a result of this change from infinite square well to finite square well. Draw diagrams. Okay. So I will start so this is an open-ended question, and I ask you for 3, even though I'm really looking for 1 or 2 main things, hoping that in answering 3, you will have, brought up 1 or 2 important things. So let me start with the most important one. Most importantly, in the infinite square well, the quantum number n was unlimited. You could have arbitrarily high allowed energy. With the finite square well, the number of states and quantum number n would be limited, so that the highest allowed value En is less than U naught. Otherwise, it's not a bound state. By the way, when you go from bound to unbound state in finite square well, you can see this thing that's proven in quantum mechanics, that bound states have discrete quantized energy levels, and free particles can have a continuum of energies. So once you are outside the well, then energy is continuous. You are not limited to a kind of discrete levels. So that's the most important one. And what else would I look at? So I guess for the bound states, their probability outside the well does not immediately go to zero. Instead, it undergoes exponential decay that's determined by the difference between U naught and now lower E. That's the second thing. What's the third thing? So the solutions will still be like even or odd with respect to like middle of the potential. So that's not a change. Or the wave function psi of x and allowed energies. I guess inside the well, for the allowed energies, En is not equal to n squared h squared over 8 times n times l squared, because the possibility of some of the wave function in being in the region where the potential energy is greater than E, because the possibility means the energy eigenvalue shifts a little from the infinite parallel potential where this wasn't possible. It's a much smaller change than 1 or 2, but well, that's I guess 3. Don't know what else I was thinking of. I guess we'll have to look at the solution to see what I thought of back then that I'm not remembering, and I'm not going to remember, and I don't have to. I listed the 3 significant changes, and the 2 of those are the ones that I cared about. I remember it because I wrote the question. All right, so this is a relatively easy question. You know, I actually didn't have to do any calculus. I could have just gotten through this through sheer memorization. I think I've complained about this before, that a lot of our homework questions end up being kind of easy, especially compared to lectures, because I do want you to learn the more sophisticated stuff about quantum mechanics and special relativity, but I don't have as many questions available from the textbook. One, two, there are some questions I have written in the past, and they always come out a little bit hard. So I'm a little bit worried about doing it. Let me paste in the work. I guess I can do that now rather than trying to burn through that time. So this is A. Again, you should really organize your work way much more than what I'm doing now. Right now, I'm just pasting in what is a scratch work, and I shouldn't be doing it. Do what I preach, not what I practice. If this was a class I was taking, then I would totally organize my work before submitting it. Because, I mean, you know, okay, if you don't do it, I don't think anything bad will happen to you. But I do recommend that you take some time to organize your work. All right, so we'll submit it, and then let me go into my instructor view and then see if I made any serious mistakes here. So I guess I can close this now. Going as instructor. I wonder if I do this on this shared screen, would I have to change anything? Oh, yeah. I think I would probably have to. There are some people who've done the timed assessment already, I think, before test the student. So this is what I should do. I should do grades. And then click through to the one that test the student did. and then bring it back. Okay, so this is the test the students attempt as viewed from instructor view. It's quite similar to wait, save work and that's gonna mess it up. Yeah. It's doing that because I'm logged in as instructor over there. That kind of messes up stuff here. Let me see. Did I submit it? Okay. I think it's fine. Yeah. So okay. So this is the test student's own view of his own work, and there's no answer key here because it's not due yet. Past the due date, the answer key will pop up. Now I can just using my instructor view just show the answer key. So let me do that for each of the questions and make sure I didn't miss anything. Yeah. Oh yeah, and that this doesn't apply because the potential goes to infinity. It's one of the loopholes. That's why the boundary condition for the smoothness of the wave function is a weaker condition because there are loopholes. Oh, I talk about general solution. I don't think I have to talk about general solution. Applying the boundary conditions, yeah, that. So with those conditions, now I kind of did it backward. I just sped out the memorized the solutions, which weren't wrong. And the same thing with the energy. I did it in terms of Planck's constant instead of the reduced Planck constant because I happen to have numbers memorized a little bit better for just regular Planck. Yeah. Yeah, I think that's fine. Part C, the sketch of the probability density. Yeah, still looks like a sine wave, but also the double the frequency is 0. Yeah, I think that's right. Yeah, those are the pictures that I was drawing before. I guess I could have talked about hump. But I have the sketch of the solution. Okay, part D is the complex one. A complicated one. It's not complex. When it's a bounded state, you can always choose a real solution. So, but as I was saying, it is an open-ended question, and I ask you for a little more than what I care for. 3 instead of 2 or 1, in hopes that in trying to answer 3, you will at least hit upon those 1 or 2. So yeah, change number 1. This is what I said. There's an infinite number of solutions. Quantum number is unlimited. Now here it's limited. Change to outside Schrodinger has a real yeah, so this is basically what I was saying about probably the outside the well is not immediately 0. Instead it'll exponentially decay. So there's a small thickness where you have some probability of changing finding the particle. And change it 3. Yeah, I mean, it's not exactly my 3 here, but thought this was a bit repetitive of what I had to consider for 1. Um, but yeah, no mistake, nothing major that I missed. I guess that's the demo for this. Thank you.